Now let us discuss some of the fundamentals of thermodynamics, and uh, in this lecture we will be discussing those fundamentals that are the PVT surfaces. PVT stands for pressure, volume, and temperature. Surfaces. What is surface? When we look into an normal graph, it is usually a line because it is usually drawn over a 2D space. But in this, we are talking about PVT, that it is three-dimensional pressure, volume, and temperature. We will be looking into the effect of pressure, volume, and temperature simultaneously on a pure substance. That's why it will generate a surface instead of a line. That's why it is called PVT surface. However, please don't confuse yourself and be relaxed because it is nothing difficult. We will be usually discussing no more than two variables at a time. This will result us to simplify and to generate a line graph instead of a surface, and we will at the end we will discuss, we will enhance, and we will look into the surfaces as well. Then we will be discussing the two-phase states, that is when our pure substance exist in the form of liquid or vapor, solid or liquid, or more than one phases. And phases are solid, liquid, and gases. These are three phases of a pure substance that a pure substance can possess at any under any certain pressure, temperature, volume, and other thermodynamical properties. So these we will be discussing states, definition of phases, and then we will be discussing two-phase states, as I already said, and beyond that is liquid and solid states. Then superheated vapor state. Superheated vapors. What are superheated vapors? Superheated vapors are vapors. Uh, but what's the difference? Superheated vapors possesses more energy than a simple saturated vapor state. So superheated vapors are vapors as saturated vapors, but they carries more energy. The pressure might be higher than the pressure might be lower than the saturated vapors. Temperature might be higher than the saturated vapors, and these conditions, volume may be lower than volume may be higher than the saturated vapors. These are the conditions that make a vapor and convert it into a saturated superheated vapor. Uh, then we will be discussing what is ideal gas. Superheated vapors are mostly ideal gases, yeah, but it's not like that. Said ideal gases are superheated vapors. All superheated vapors are not ideal gases. We cannot consider all the superheated vapors as ideal gas, but all the ideal gases are superheated vapors. You experience here around you, and it comprises of a combination of different gases like oxygen, nitrogen, carbon dioxide, carbon monoxide, and other different noble gases. All these gases are superheated vapors because their boiling point at the atmospheric pressure is much more lower than the normal room temperature. That's why these gases exist around you in the form of superheated vapors. So all the gases are superheated vapors, but all the superheated vapors are not ideal gases. Then we will be discussing compressibility factors, equation of states, and then how to look into the computerized thermodynamic tables. Here on this slide, we can see a piston cylinder assembly, and the piston cylinder assembly is specifically a constant piston cylinder assembly. In this configuration, whenever there will be a change in weight upon the piston, you can see the stacked weights on the piston top. Whenever we increases this weight, then there is a change in internal pressure because of the external forces. However, if the external weights remain constant, then internal pressure remains constant because the piston will move up and down to compensate the internal pressure, as long as, and this motion will be as long as the internal pressure comes equal to the external pressure. So this piston constant piston cylinder assembly, and we assume that there is no friction between piston and cylinder surfaces. So it's a frictionless piston that is used to maintain internal pressure as of the external pressure, and we are exerting the external pressure by means of weights upon the piston. Now let us examine what will happen if we uh, input some energy to the system and discuss the constant temperature boiling process. However, before that, let us define some conditions that the water is at 101 kilopascal, external pressure is 101 kilopascal, that is equal to 1 atmospheric pressure. The liquid is initially at the room temperature, that is 25 degrees centigrade, and here we heat the water and observe the states and observe what will be going inside in terms of pressure and temperature. So what we are seeing here at the lower right corner is a graph of pressure and temperature. It is something sometimes also called saturation pressure temperature graph, that indicates what is the saturated pressure at certain temperature and what are the temperature for saturation at certain pressures. So by continuing, we gonna heat the system, and what will be happening first, let us assume that all of the pure substance, that is water, inside the cylinder is existing only in the form of liquid. It's obvious that water exists in the form of liquid at room temperature and at atmospheric pressure. Therefore, this is the initial state which we are discussing. Then what will be happening if we add in some heat? If we add in some heat into the system and heat it, it will increase the temperature of the water up to 99.6 degrees centigrade. Why 99.6 degrees centigrade? Because at atmospheric pressure, the boiling point of water is 99.6 degrees centigrade. Now, if we reach this point where the temperature reaches 99.6 degrees centigrade, however, the volume will not be increasing up to this point. We already know that if we have a cup of room temperature water and we place it in a microwave and heat it up so for certain seconds, the and when we take out the cup out of the microwave, the volume does not increase. It's not like that we put in one cup of water and heat it for a few seconds and when we get the cup out of the microwave, it is overflowing the cup. No, it is most likely not the case. It will happen if we continue heat for a long period of time, and the input heat causes the temperature to increase beyond the boiling temperature. Only then. But up to the boiling point, the volume does not increase. That is why we also know that the density of liquids does not change upon variation of temperatures. Density does not changes. Therefore, density, because the density is the reciprocal of volume, specific volume. That's why if density does not changes, we can say that volume does not change. And we also have observation that it doesn't change for a liquid if we increase the temperature by few degrees below the boiling point. So what will be happening if we are adding in the heat in this system and temperature is rising but the volume is nearly constant? It will increase but insignificantly. Only the temperature will increasing. Now if we continue the heating process and temperature increase, temperature reaches 99.6 degrees centigrade at 101 kilopascal, that is atmospheric pressure. Now water will start boiling inside this piston cylinder assembly. So when water will start boiling, it will be generating vapor at a much exaggerated pace than it was generating when the liquid was possessing all of the volume. So evaporation takes place at all temperature, but boiling point is when we reaches the internal pressure that is equal to the external pressure. And what is internal pressure? Internal pressure for in this case is vapor pressure. So boiling point is when the vapor pressure reaches the external pressure. So therefore, up to the boiling point, only the temperature is increasing, not the volume. Now, when water starts boiling, its temperature will remain constant, 99.6 degrees centigrade. However, now its volume will be increasing because now vapors are being generated at a high pace. So the piston cylinder assembly will grow in terms of size. In terms of size, its volume will be growing up to when when all of the liquid is converted into vapor. Now, beyond this point, if you continue to further heat the system, now because all of the volume is occupied by vapors, now temperature will increase and volume will increase as well. So this is the constant temperature, the constant pressure boiling process. We can also convert this configuration into a constant temperature boiling process. Uh, we can put this assembly in some sort of temperature controlled environment, and we forcefully move the piston upward by means of any force, mechanical force, while keeping the temperature constant. Now the pressure will be varying. So initially the volume is small and pressure is uh, is at its highest point. Now if we forcefully move the pressure piston upward, what will happen? That the internal pressure drops. Internal pressure drops and water will start boiling because of lower in vapor pressure. So vapor will generate, and it will continue to generate until the vapors are in such a quantity that it exerts pressure that is equal to external pressure. So we can also boil water or any other pure substance at a constant temperature by means of a force. We increase the volume, and this decreases the internal pressure. When internal pressure decreases, it will start boiling. And the same process can be repeated in a constant temperature configuration as well. Now, if we look into this graph, what is this graph? That it show us this line, this is saturation line, and what does it tell us? That for each and every pressure there is a temperature at which boiling will take place. Similarly, there is, for each and every temperature there will be certain pressure at which boiling will take place. For instance, in the first case, we have seen that what will happen if we continue to add any heat? What will be the variation of temperature? When will it, at what, if we keep the pressure constant, at what temperature it will be boiling? Similarly, if we keep the temperature constant, there must be a pressure at which it will boil. If the pressure is higher, then it's not boiling. If pressure is lower, then it's boiling. So for each and every pressure, there is a temperature at which pure substance boils, and for each pressure, there is certain temperature at which a pure substance boils. Now we have to discuss this graph in detail. This is called pressure temperature graph, and there are three zones in it. One is solid, liquid, and vapor zone. This graph also tells us about the sublimation. It also tells us about critical point. It also tells us about fusion. It also tells us about the saturation. Now, if, for instance, if we have a solid material, like for instance pure substance in the form of solid, let us consider the example of ice, and we have kept it on, let's suppose this is the atmospheric pressure. At atmospheric pressure, this is 0 degrees centigrade. For instance, if we have pressure of 101.35 kilopascal, that is 1 atmospheric pressure, and the temperature is minus 20 degrees centigrade. Will the ice boil? No, ice will not. Will the ice melt? No, the ice will not melt. It will only melt if we continue to increase temperature. We move toward this line and crosses this line. When we cross this line, now it will be liquid. But you know that before becoming a liquid, it coexists in the form of solid plus liquid. If you put ice cubes into a glass filled with water, initially The ice will not melt in a fraction of no time and just convert into a liquid momentarily. No, instantaneously there will be no melting. It will start melting, but it will coexist with liquid water inside glass. Now the temperature of liquid water will keep on decreasing, and the ice will continue to melt. This coexistence is depicted in this graph upon this line. Upon this line, and when we continue to increase the temperature from 20 degrees centigrade and reaches this point, then it will be coexisting in the form of solid and liquid. It will continue to melt on the same temperature at 0 degrees centigrade. That's why we call it ice bath. If you put some amount of ice cubes into water, and for certain experiment we want to maintain the temperature at 0 degrees centigrade, we just have to have some liquid water, we put in some ice, and it will generate an ice bath. Now the temperature of this ice bath will remain 0 degrees centigrade until all the ice melts down into a liquid. If we keep on adding ice into this ice bath, the temperature will remain constant. However, the ice will be coexisting with liquid water. Therefore, if we look into this graph and we study in detail, it will let us know what is the fusion temperature at which solid coexists with liquid, what is the saturation temperature, saturation pressure at which the liquid coexists with vapors, what are the temperature and pressure sets at which superheated vapors exist, what is the triple point at which liquid, solid and vapors coexist at a single point. It's called triple point because all the three phases are coexisting. That's why it's called triple point. You must have seen that there is solid, liquid and vapor phases shown in this PT diagram. So when solid crosses this boundary and becomes liquid, complete liquid. When liquid crosses this boundary, it becomes vapor. When solid crosses this boundary, it becomes vapor. But what if we reach this point, exactly this point, then the pure substance will be coexisting in all three phases, and because of it, it is called triple point. It will be in the form of solid, liquid, and vapors at the same time. So it is called triple point. What is critical point? It will be more easy to understand triple point when we discuss PV diagrams and further lecture in the next upcoming slides. Therefore, what does this graph tell us? It tells us a number of things. There's solid, and upon certain temperature, if we decrease pressure, the solid will convert into vapors without converting into liquid and then into vapors. It will directly convert from solid into vapors. It is called sublimation, the process of sublimation, directly converting a pure substance from solid into a liquid. It's sublimation. Then there's a saturation line. We have discussed the uh, constant pressure boiling process in previous slides, and we have seen that the water will continue to boil up to a certain point when it becomes pure vapor, and up to that point the temperature will remain constant and liquid will be coexisting with vapors. So this is depicted, or this is presented upon this line. Upon this line, this is line of saturation. Here is liquid, here is pure vapors, pure liquid and pure vapors. So if we have certain pressure and we have liquid water, for instance, we increase the temperature up to when we reaches this line. Now what will happen, that liquid will start vaporizing and it will continue to vaporize until the complete pure substance is in the form of vapors. At that at that moment at, at that moment it crosses this line. Upon this line, the liquid and vapors coexist in the form of saturated vapors. If we further continue to increase temperature and putting in heat, the temperature will increase and now the vapor will cross this line and become superheated vapors. So all the vapors in this region are superheated. All the vapors in this region are superheated vapors. Only saturated vapors on this blue line. So the table beneath the graph also show that what are the triple point for different materials, what should be the specific pressure and temperature if we get our system into that temperature or pressure. For instance, carbon dioxide at 7 megapascal, at 7.4 megapascal, the temperature is 31 degrees centigrade. The carbon dioxide will be coexisting in all the three phases and it will be a triple point. For nitrogen, it's minus 147 degrees centigrade and 3.4 megapascal. The triple point for a nitrogen is at minus 210 degrees centigrade and 12.5 kilopascal. For oxygen, it is minus 219 degrees centigrade and 0.15 kilopascal. So here we have triple point temperature and triple point pressure for these materials. For water, it is 0.01 degree centigrade and 0.6113 kilopascal. So normally we have atmospheric pressure that is 101 kilopascal, 101.35 kilopascal, and you can see that here pressure is 0.6113 kilopascal, nearly 101 kilopascal below the atmospheric pressure, and the temperature must be 0.01 degree centigrade to achieve triple point. If the now if the now Here we have our pressure. So this is saturation temperature for this P saturation. So if we have a system in which temperature is more than this saturation temperature, the substance is in the form of superheated vapors. If we have certain, if we have our system at this temperature, for instance, and this pressure, PS in red color and TS in red color, if we have controlled temperature at TS, T saturation, that is shown in the red color. Now, what will happen if we decrease the pressure? So our system will move from this point downward over here, and this is the region of superheated vapors. So if we have a system and pressure is lower than the saturation pressure, then the vapors exist in the form of superheated vapors. So temperature must be higher than the saturation temperature, pressure must be lower than the saturation pressure, and volume should be greater than the volume occupied by the gaseous phase, pure gaseous phase. Then the system will be in the form of superheated vapors. On this slide, there are two graphs, one for water and one for pure carbon dioxide. We can exploit this behavior of pure substance that is converting of solid into liquid and then into gases. We can exploit this behavior, and we can use the pure substance for our engineering purposes. For example, uh, it is usually water that converts from ice to liquid and then into solid at a small atmospheric pressure, but not for the carbon dioxide. For example, each and every material has different characteristics and different behaviors. We can see this difference in behavior of water and carbon dioxide, and we can see that for the water this line is straight, for the carbon dioxide it's not straight. It takes this turn and moves toward right when we increase temperature or pressure. But the same graph, that is pressure temperature graph, for a water is quite different than pressure temperature graph of a carbon dioxide. Just forget about this region. It is the crystallic structure of ice that changes if we change the temperature and pressure sets. So only consider for the understanding, only consider this one. Okay, only consider this part of the graph, and you can observe clear-cut behavioral variation when material varies from water to carbon dioxide. So what will happen at 101 kilopascal? 101 kilopascal is nearly zero point 0.1 megapascal, and 0.1 megapascal is over here, nearly in this range. And if we have temperature over here, pressure, the solid ice will cross, if temperature increases, ice will cross this boundary and become liquid. And then if temperature continues to increase, it will cross this boundary and become vapor. However, this is for a carbon dioxide, its pressure in the in kilopascal range. So for a kilopascal, 10 at atmospheric pressure, it's 101 kilopascal. Now, because of this variation in behavior of carbon dioxide as compared with the water, if we have certain carbon dioxide ice, amount of carbon dioxide ice, and temperature increases, it crosses this boundary and it will get into this region, whereas the liquid region over here. Okay, so it will directly go to the vapor phase. That's why it's called dry ice. That at atmospheric pressure it sublimates and it directly converts itself into vapors from solid ice without wetting any surfaces in the form of liquid carbon dioxide. So we exploit behavior of materials and we use it for our engineering purposes. What is over here? If we rub it down in this region, it is only difference of crystalline structure of ice. So I have ice 1, ice 2, ice 3, ice 4 and ice 4. 5, even ice 7 is all shown in this slide. If we change, all of these are ices. So if we change temperature or pressure, so most of the time pressure for ice, if we increase the pressure over ice, then it will change the crystalline structure of ice, and that differentiates between ice 1 and ice 2. If we have normal ice, as we have in our homes, and we increase the pressure, we put it in some chamber and we continue to pressurize the chamber, the crystalline structures, the arrangements of molecule inside that ice varies, and when it varies, it converts this ice into ice 2 and ice 3. Now, so ice 1, ice 2, ice 3 is are there. All of these are certain type of ice, but with having different crystalline structures. Now let us look into the constant boiling process in a temperature volume diagram. How to represent a constant boiling process and how to study, interpret and represent a process state on TV diagram, temperature volume diagram. What we have seen is a temperature volume diagram for water, and most of the traditional engineering pure substances that are being used in engineering, like water, uh, carbon dioxide, argon gas, and other pure substances, they exhibit similar kind of behavior. There might be difference in some values, but the overall pattern that pure substance adopt exhibit is nearly same. So let us consider the constant boiling process on. But initially, let us see what the graph and how to read this graph. On a y-axis we have temperature, and x-axis we have the specific volume. Specific volume, you know, it's reciprocal of density, and it's the volume per unit mass. How much a 1 unit pure substance of mass exhibits the volume, how much volume that pure substance exhibits at certain temperature is called specific volume. Not only on a specific temperature, but under certain states, combination of pressure and temperature. That's the control specific volume. We have already discussed it in on campus classes. So on y-axis we have temperature, and on x-axis we have volume. And these different graphs, that is a line ABCD, a line EFGH, the line IJKL, MNO, and PQ. These lines are lines for different pressures. Recall the last slide, and we have discussed a constant pressure boiling process, and that there is no change in pressure during the complete experiment. The whole experiment was conducted under the controlled amount of pressure. We have put a certain amount of mass of piston cylinder assembly, and that mass is kept constant during the entire experiment. It means that there is no change in pressure during the experiment. So these lines are for different pressures, and these pressures you can note down over here. These are the pressures for different. For the first ABCD, let us discuss this curve first, and then move on to other curves. For this curve, we have assumed that the initial temperature is room temperature, and the pressure during the complete experiment is atmospheric pressure 101 kilopascal nearly. So 0.1 megapascal. So this 0.1 megapascal remains the same for entire length of the experiment. Only the temperature and volume changes. Now recall that we have already discussed that when we heat up the piston cylinder assembly, the temperature of water will increase from room temperature to 99.6 degrees centigrade, and this is the boiling point of water at atmospheric pressure. So therefore it will only the temperature will increase during this initial phase of the experiment. Volume will nearly remain constant, and this can be seen over here. If over here, that only a slight change in volume occurs during this initial phase, when the water is being heated from the room temperature to the boiling point. But when the boiling starts, the temperature remains constant, and up to when? Until it reaches a point where complete liquid water is converted into vapors. Up to this point, only the volume will increase while the temperature remains constant. Why? Because when the evaporation occurs, it is a constant temperature process. Usually the heat given to the molecules take away this heat that we have been providing to the experiment using a burner or any kind of heating element. Molecules on the surface take away this heat and leaves the liquid surface, thus taking away the energy with themselves. Now the remaining energy inside the liquid is nearly constant, and the more energy we provide, the more rate at which we energy provide, or the bigger the rate of energy we are being providing to the experiment, and the greater will be the evaporation rate. But when the molecule leaves the surface, the overall energy of the liquid decreases because of the molecules are taking away the energy we are providing to the experiment. Therefore, it remains a constant temperature process up to when there is no liquid molecule left and complete water is now in the form of vapor. Now, if we provide further heat and we keep on heating our apparatus, then the volume increases and temperature increases as well, because now there is no evaporation process. Now vapors will heat up, and they will become superheated vapors. So another aspect of this curve is that there are three regions here. The region over here is superheated. Over this line is saturated vapors, and over this line it's saturated liquid. Here it is compressed liquid in this zone. Here saturated liquid. Let me draw it with different colors. Initially, this is the compressed liquid zone. Okay. Now this line is a saturated liquid line. Here it is liquid plus vapor, and then this line is pure saturated vapors, and then this side is superheated. This complete zone is superheated. So there are five different regions shown on this graph. First is compressed liquid, then saturated liquid, then liquid plus vapor, then saturated vapors, and then superheated vapors. Now after the the moment at which all of the liquid molecules turns into such vapors, it is called saturated vapors. If we further provide the heat, these vapors will turn into superheated vapors. So therefore this is how we interpret this diagram, TV diagram. Now if we repeat this process and increase our initial pressure that we will be going to keep constant during this experiment. If we increase this process from 0.1 megapascal to 1 megapascal, now we know that with the increased pressure the boiling point increases, as we have seen in the last slides. And let me draw it here again. This was PT diagram we have discussed in last slide. So if we increase the pressure from this point to this point, the boiling temperature increases. So increase in pressure increases boiling temperature. So this can be seen over here, and that we increased our pressure and the temperature increased from 99.6 degrees centigrade to 179.9 degrees centigrade. This is now a jump in the boiling temperature. However, the phenomena remains same. and until it is heated up to a point where all of the liquid turns into vapor. Temperature remains constant, and beyond this point, the superheated vapor uh, will start generating, and temperature and volume both will increase. If we increase our pressure from zero point 0.1 megapascal to 1 megapascal to 10 megapascal, then again the boiling temperature will increase, and now this is constant temperature boiling, and then superheated phase. If you continue to increase the pressure up to 22.09 megapascal, now there will be no boiling process that occurs on this pressure. Now what will happen, that you have observed that this length is decreasing. The length of boiling is decreasing with increasing pressures. There will come a point that beyond this pressure, or at this pressure and beyond, there will be no constant temperature boiling process, and the pure substance will instantaneously turns into from liquid to vapors. Not instantaneously, nothing happens in no time, but as compared to previously studied constant temperature boiling process at lower pressure, the boiling at 29.0 degrees centigrade happens momentarily. How this happens, that at this high pressure, when we supply heat to our apparatus, the boiling, the density of the liquid starts decreasing from the very first. You can see that there's a negligible increase in initial phase of experiment for the pressure 0.1 megapascal, 1 megapascal. However, if we look into this from what we are studying currently, you will observe that there's relatively substantial amount of increase in volume as compared to the previous cases. Here we have substantial increase in volume, that the density starts decreasing from the very first moment we started the experiment. Now when it reaches the point N, it is nearly they are saturated vapors, and after this point they get superheated vapors from this region and beyond, from N to O, where N is not included in this. So for a subset, for a N to O, this will be superheated vapors. So this is known as a critical point. We have already seen PT diagrams in last slides, which is done over here, and you have observed that there is a point over here that is called critical point. This is critical point that I have said that we will discuss it in later slides. So this is a critical point. Now beyond this critical pressure, there at this pressure and beyond, there will be no constant temperature boiling process. So the saturation line ends here. So you can observe the saturation line. This saturation line, if we let me highlight it, this saturation line ends at this point. That's why it ends at this point, because beyond this point there is no constant temperature boiling process. Therefore, this the pressure that we usually most of the engineering application, mechanical engineering application, we don't take our system to that much higher temperature pressures, but for the completeness we must study it. So therefore, it is now clear that what is critical point, and how to read a TV diagram, and how to set up apparatus, and for constant boiling process at different variable pressures. So this is the graph for water, but the overall behavior of engineering materials or pure substances remains the same, irrespective of the material, like water or nitrogen or methane or any other carbon dioxide, argon gas. All of they exhibit similar kind of behavior, but the values will be different. For instance, at 0.1 megapascal, the boiling of the carbon dioxide might take place at even in negative temperature, like negative 35, something like that. I don't remember the exact boiling point of the carbon dioxide at this pressure, but the only difference will be the values. The behavior will remains the same. So this is how we draw and we interpret and we depict. What next? We will be discussing different volumes for this, for how to label this diagram in more detail. Now let us study how to interpret the data given in thermodynamic tables, and how they correlate with the PV, TV, and PT diagrams. Uh, for instance, let us recall the last slide, and recall the temperature volume diagram. In this diagram, we have studied that there are five regions: so, compressed liquid, saturated liquid, liquid plus vapor, saturated vapors, and superlated vapors. So these are five regions that were present on TV diagram. Here again we have TV diagram, and let us correlate how to interpret the volumes that are given in thermodynamic tables in the form of VF, VFG, and VG. So when the boiling starts, when our system reaches this point, that a constant boiling temperature may start. So volume is this volume is VF. That if the unit unit mass of a pure substance is in the form of saturated volume, saturated liquid, how much volume will it occupy? It is called VF. And when it reaches the end point, when the boiling reaches the end point, this point, uh, so let me redraw it. This point, this is the volume that will be occupied by saturated vapors when complete, when the entire whole mass is in the form of saturated vapors. How much volume it will occupy, it is known as Vj. And Vfg is not a physical volume, it is the difference of Vg minus Vf. So it is length of this line. This line length of this line is Vg minus Vf. It is known by Vfg. So we can find these volumes. For instance, if we have water at 5 degrees centigrade, and this is saturation pressure for 5 degrees centigrade. If we have a pressure of 0.8721 kilopascal, then the boiling will start at 5 degrees centigrade. Or we can say that if we have 5 degrees centigrade and our pressure reaches 0.8721 kilopascal, the boiling will start. If we have greater pressure, higher pressure, then there will be boiling at 5 degrees centigrade. For instance, if we look down over here, if the pressure increases, then this boiling temperature increases. So if we have 5 degrees centigrade and we have 1 kilopascal, then there will be no boiling occurring, because since now pressure is greater than pressure is 1 kilopascal, that is greater than 0.8 megapascal. So the temperature was of saturation or the boiling temperature will be higher, so it will not boil at 5 degrees centigrade. So we have different sets of boiling points for different temperatures, in the form of pressure, in the form of temperature. So if we have a specific temperature and pressure, then the volume occupied by the liquid is Vf, volume occupied by the vapors, saturated vapors, is Vg, and Vfg is difference of Vg and Vf. So if you have a system, for instance 15 megapascal, and you have this system, that a system is at 15 degrees centigrade, and the pressure is 1.5 kilopascal, then it has already reached the superheated phase. Now because the pressure is lower than the saturation pressure, so the system has already reached the superheated state. If we have 15 degrees centigrade and 2 megapascal, then boiling has not started yet. And if we have if we have 1.70 of 1.705 kilopascal and 13 degrees centigrade, now the temperature is low than the saturation temperature or the boiling temperature, so boiling has not started yet. Now the fourth case is if we have 1.705 kilopascal and 20 degrees centigrade. Now temperature is greater than the saturation temperature on a specific pressure, that is 1.705 kilopascal. Now temperature is 20 degrees centigrade. Now the system has already reached the superheated state. So this is how we interpret the thermodynamic tables, and how we correlate our phase diagrams with it. Now the second one is PT diagram. If we have already discussed it, but if we have certain pressure, we have certain boiling temperature for it. If we lower our pressure, the boiling temperature decreases, and if we increase the pressure, boiling temperature increases. If we have certain temperature over here, for instance our system is over here, so, and we look into this diagram, we will see our system is over here, pressure was this high, saturation temperature was this, temperature of system is greater than saturation temperature, so the system is in superheated phase. This is the line of saturation in PT diagrams. If we have for instance 15 degrees centigrade, and let us draw it again. Now you can see if we have a saturation pressure, and the system is exactly on the saturation temperature, then it will be on this line as down on the circle. If the temperature is greater, it will be in this region. If temperature is lower, it will be in this region. And if the some temperature much lower, then it will be solid instead of liquid. So this is how we interpret our diagrams and in terms of our thermodynamic tables.